Sophie? No. Dito. Dito, come here, my kitty. Okay. Say hi, Sophie. All right, it's 8:30, so let's go ahead and get started. All right, good morning, everyone. Thanks for accommodating the last minute change. I know is kind of last minute yesterday, but basically my wife called me and she said the garage door won't close. So there's something wrong with our garage door. So I had to call a repairman to come out and fix it. So right now the garage door is just kind of wide open. It just kind of refuses to close. So yeah, we need to get that fixed. So thank you everyone for being accommodating today. And the lecture we posted on YouTube as usual too, so you can definitely view it there as well. Okay. All right, so the plan for today is we are going to go and continue our lecture notes on probability statistics. And so I believe last Tuesday we left off on confidence intervals. Okay. And so we'll continue on with that. Regarding the exam, I haven't had a chance to start grading it yet, but it is on my to-do list today. And so I am going to start today, and I'll definitely have it ready by Thursday. And so by tomorrow night, you should know what you have, just because I'll have it graded by then. And then Thursday, I'll bring it to the class. And so if you want to come by on Thursday to pick up your exam, you guys can do that. Okay. All right. And so other announcements. Homework 7 has been posted. This is the final homework for the class. Okay, I think probably everyone got a notification from Canvas about that. So the homework 7 has to do all with probability and statistics. So I don't think it'll take very long. It's relatively chill homework assignment, and it's due next Friday. So I believe that's like May. What is that? That's May 12th. Okay. All right, and so with that, we are very quickly winding down the semester, and so we have just two more weeks to go, and so we have 2 lectures this week and 2 lectures next week. I'm planning to finish up all the content for the class by next Tuesday, so we have only 3 more lectures of actual new content, and then next Thursday, what I wanted to do is I wanted to have a review for the final. Okay, and so later today, what I'll post is I'll post a study guide for the final exam. Okay. And so that study guide will be your kind of your first stop resource for the final exam. Okay. So it's actually been a while since I've given a final exam. Usually I do final projects for a lot of my classes, but usually my policy for the final exams is that it is cumulative, and so you are expected to know content from basically everything in the class. But I don't put everything on the final exam. That's literally impossible for a 2-hour exam to cover to put a whole semester's worth of content on a 2-hour exam is impossible. And so what I usually do is, on the study guide, what you'll see is that, among the topics that are on the study guide, it's not going to be a full list of everything that we covered in the class. It's going to be a curated list. And so I'd say you're probably going to be responsible for about, 2/3 of the total amount of content in the class. Okay. So I'll cut some contents. I'll cut weeks of content away from the final exam, just because realistically, I can't put the whole thing on the final exam. And so, I'm not going to ask you guys to prepare for all of that, just because not everything is going to be there. Okay. So definitely use the final study guide. So I think this final exam study guide is probably going to be more important than the midterm ones, just because you need to look at the study guide to know what's going to be on the exam, what's not going to be on the exam. Okay. All right, and then just like the second midterm, I was able to talk to a couple people after the class. It seems like the practice exam was very helpful for everyone. So I'm going to do the same thing. So I'll post a practice final exam onto Canvas. Probably I'll just give you the last final exam that I gave, and then and then you can use that for practice. Okay, so you can expect both of those up by today. So the practice final as well as the study guide for the final. Okay. And remember, I really want to emphasize that the final exam is cumulative. So, I am going to put some differential equation stuff from the beginning parts of the class, as well as, the previous exam. Probably from the previous exam, we'll probably only do Fourier, maybe just Fourier series. But but it is going to be, cumulative. And so you are expected to know stuff in the beginning, just not absolutely everything, just because I can't test you on everything. Okay. All right, and so that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. And so let's talk about confidence intervals. That's where we left off last time. Okay. All right, so we left off on this idea of confidence intervals last Tuesday, and let's just kind of remind ourselves what it is. Okay, so confidence intervals, this has to do with whenever we are performing an experiment to determine the value of a certain quantity. Okay. Okay. And so when we perform these experiments, and we want to determine the value of a quantity, oftentimes we want to express or we want to quantify how confident we are in that prediction. Okay. So let's say, for example, that we want to estimate the the average height of all Cal State Fullerton students. Okay. And so there's, there's lots of different ways you can do this. And so, the most confident way you can do this is you can take all the students that attend Cal State Fullerton, you can measure their heights and you can get a number, and then you can just average them, right? So that would give you a fairly confident measurement of their heights, right? Another way you can do it is you can measure yourself, and maybe you can measure your two friends in the class, right? And you can average those numbers, okay? And so among the three of you, you would get a number, you'd get a figure for how the average height, and technically you guys are all Cal State Fullerton students, and so you would get another number from that. But you would say that among the three of you, computing the average height from just three people, you're not really as confident in that measure as compared to everyone else. Okay. And so confidence intervals are kind of our way to kind of formalize that, and so kind of formalize our confidence in a particular measurements. Okay. 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 All right, and so there's two parts to confidence intervals, and so there's the actual measurement itself, as well as kind of the upper and lower bounds. Okay, so that's kind of how it's displayed. Is it kind of shows you an upper and lower bound for the measurement, and there's a degree of confidence that gets associated with it. Okay. Okay. So for example, when we talk about confidence intervals, you would see something like this. Okay. And so let's say that I want to perform an estimate for my commute time. Okay. And so if I were to put a confidence interval on my commute time, it would look something like this. Okay. Okay. All right. And so let's say that we want to have a high degree of confidence. So let's say that we want to have like a 95 degree of confidence. Okay. Okay. And so if you were to ask me to estimate with 95% certainty kind of the upper and lower bounds of my commute time, maybe I would give you something like this. Maybe I would say, I'm 95% confident, or in other ways you can say it is 95% of the time that I come to school, my commute time is going to be between, maybe 26 minutes and 34 minutes. Okay. And of course, the average between the two is 30. And so what I can say is that on average, it would take me 30 minutes to come to school. And with 95% confidence, that varies anywhere between 26 and 34. Okay. Right. So generally speaking, the higher the confidence, the wider the interval, right? Because you're accounting for random effects that can occur, right? And so if I were to increase this, and so let's say that if you ask me, with 99% certainty, so 99% is almost 100%, but it does leave a little bit of leeway there for some variance, for some randomness. Okay. If you were to ask me to give you a 99% confidence interval for your commute time, then I would give you a wider range because, of all the random things that can occur that we talked about. So things like traffic, like pedestrians, stoplights, construction, all that stuff. Okay. And so, generally speaking, the higher your confidence, the wider your range is going to be. Okay, because you have to account for all of those uncertainties, right? Because with the 95% confidence interval, what we're saying is that, there's a 5% chance that my commute time is going to be outside this range. Okay. When you increase your confidence, you're basically, accounting for more uncertainty. Okay. So maybe the 99% confidence interval might be something like, we're going to have the same average. And so the average is also still going to be 30 minutes, but maybe we increase this to maybe like 20 minutes to 40 minutes. Okay. And so basically there's only a 1% chance that my commute time is less than 20 minutes. Well, I mean, technically it's 0%, but there is a 1% chance that my commute might take over 40 minutes because, maybe there's an accident on the freeway, maybe I get into an accident, there's a lot of things that can occur. Okay. The opposite is true as well. And so maybe if we go down in confidence, then we can kind of tighten our interval. Okay. And so let's say that we have a 50% confidence interval. Okay. Right. And so around our mean value, maybe we have a 50% confidence that maybe our commute time is between 28 minutes and 32. Okay. Right. So you can see here we have a much more narrow band, right? So between 28 and 32, that's only a difference of 4 minutes there. But because it's such a tight band, we only have 50% confidence that we're actually going to be within that band. Okay. Right. And so generally, the higher degree of confidence, okay. Right. So generally speaking, the higher our degree of confidence, the wider our interval has to be because because we're saying that we are this much more confident in our measurement, we have to account for more uncertainty. Right. So that's kind of the idea of confidence intervals. And so, you can have a measurement. And so our measurement in this case is 30 minutes. Okay. Okay. And so our average commute time is 30 minutes, right? But if we were to ask, how confident are you in, in your commute in terms of, how close you are to 30 minutes, then depending on our degree of confidence, we have to either make the interval wider or make the interval smaller. Okay. All right. Any questions on this? Okay. Okay. So now let's talk about how we actually compute these confidence intervals. Okay. So the numbers I gave you in the previous example were mostly arbitrary, but they still follow kind of the general trends that you see. Okay. All right. So the way that we display confidence intervals is through an interval, right? And so just like we had up there, right? And so the way that we display it is like this. And so what we say is that mu here being the true measurement for our quantity, Okay. So the true value for a quantity lies within an interval. Okay. And the interval is defined like this. And so we're going to have an upper bound and a lower bound. Okay. And so the upper bound is going to be x bar plus k. Okay. And the lower bound is going to be x bar minus k. Where x bar is the same on both sides. X bar, this is our sample mean or our measured mean. Okay. Okay. So that's the mean value that you obtain from your measurements, from your experiments. Okay. And k here, k is the confidence interval, which we'll define in a second. Okay, so how do we compute k? So k, the formula for k is very simple. And so k is equal to c times sigma divided by square root of n. Okay. So let's go ahead and define these variables. So sigma here is the standard deviation of our measurements. Okay. N here is the number of samples. Okay. And C is a parameter that is determined based on our degree of confidence. Okay. And so I guess we can say the confidence multiplier. Okay. All right, so how do we determine C? Well, so it's a lot of probability and statistics is kind of going from one formula to the next, or one formula or table to the next. So the way that you obtain C is from the following table. Okay. Okay. And so the way to read this table is you need to set a degree of confidence. So C is not the degree of confidence, it's the confidence multiplier, right? So it's I know it's a lot of terms to kind of keep track of, but I think once we do an example, I think it'll make more sense. Okay. All right. So usually for our purposes, we use the symbol gamma to symbolize the degree of confidence. Okay. And so our table looks like the following. So we have gamma and C. Okay. And so we'll make this table for starting with a degree of confidence of 90%. Okay, so this will be 0.9. Okay, so I'm displaying the degree of confidence as a decimal. Okay. That is 0.95, 0.99. Okay. We even have 0.999. Okay. So 99.9% confidence. So, a very large amount of confidence here in your results. Okay. And so for a 90% confidence interval, we have a C value of 1.645. For a confidence interval of 95%, we have 1.96. For 99%, we have 2.576. And then for 0.999, we have 3. 0.291. Okay. All right. So that's kind of the process here. And so, you kind of, you kind of work your way from the bottom up here. So first thing you do is you express your degree of confidence, then you obtain your C value. Okay. Then based on your C value and the standard deviation and the number of samples that you have, you compute K. Then from K, you compute your confidence interval. Okay. So it's a lot of steps, but at the same time, each step is fairly straightforward. It's just kind of straight, just arithmetic. Okay, so you're just either just adding, subtracting, or multiplying, right? So there's no differential equations or integrals or anything like that. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's do an example. Just so you can see it in action. Okay. So for this example, let's come up with a theoretical situation. Oh, sorry, question. So both gamma and K represent the degree of confidence, but gamma is like before modifying. So gamma is actually the degree of confidence, and so that's the actual percentage chance that you want to have attached to your interval. And so K is the actual the way that you can think of it is that you're kind of converting your degree of confidence into an actual number that's in the same units as your measurement, right? So your degree of confidence is expressed as a percentage, and then K is how much above and below your measurement is in the same kind of units. Yeah. So yeah, you can kind of think of it like that. So gamma is kind of the pure degree of confidence, and then you convert that into a value of K, which is in the same units. Yeah. Okay. All right, so for this example, let's say that we have 10 different people and we want them to measure the length of their smartphone. Okay. Okay. Measure the length of their smartphone. Okay. And they're going to use a ruler to do it. Okay. All right. So this ruler has tick marks in centimeters, and that's it. And so what we can say is that because there's no kind of smaller tick marks, what we can say is that this ruler has a precision of 0.5 centimeters. Okay. And so if we were to look at the ruler, it would look something like this, right? And so it would have tick marks like this. Okay, so this would be like 1 centimeter, 2 centimeter, 3 centimeter, 4, 5, 6, 7. Okay. Imagine it continued. I just ran out of space here. Okay. All right. And so since there's no smaller tick marks, that means whenever we perform a measurement with this ruler, then we're confident in the measurement plus or minus 0.5 centimeters. Okay. Okay. It's kind of a shitty ruler because normally you would expect a ruler to have kind of smaller denominations, but this is just an example. And so let's say that we're working with the worst ruler in the world. Okay. Okay. And so what we can say is that whatever we measure with this ruler, another way we can express this is that the standard deviation sigma is going to be 0.5. Okay. And so let's set sigma here equal to 0.5 centimeters. Okay. All right. So that's going to be important because we need that to compute the value of K in our confidence interval. Okay. We also know from this problem that we asked 10 people. Okay. And so that means we're going to have 10 measurements. And so our N value here is going to be 10. Okay. All right. And so let's say we perform the experiment. And so let's say that those 10 people obtain the following measurements. All right. So let's say the first person measured 8 centimeters. The next 3 people measured 7 centimeters. The next person measured 8. Next person measured 7. Next person measured 8. Then 7. Then 8. Then 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. Okay, so these are our 3 measurements. So half the people measured 8, half the people measured 7 centimeters. Okay. All right. And so if you were to take an average of this, and so if you were to add up all these measurements and divide it by 5, or divide by 10, sorry, we would get a sample mean of 7.5 centimeters. Okay. Okay. And so X bar here would be 1 divided by 10, 10 being the number of samples. Summation of I is equal to 1 to 10 of xi. Okay. And so we do, if we add up all these numbers and divide by 10, we see that our sample mean is 7.5 centimeters. Okay, so 7.5. Okay. All right, so based on everything in this problem right here, based on everything we know from this experiment, what we want to do is we want to compute the 95% confidence interval for the length of a smartphone. Okay. All right, so usually for these problems, you know, the degree of confidence will be given to you, and then you just have to kind of convert that. Essentially, you're converting that into a factor of K. Okay. All right, any questions on the problem setup? So, you know, any questions on kind of how we assign the values for the parameters and variables? Okay. Okay, so let's go ahead and do this problem. Okay. And so essentially, you know, when a problem asks you for the confidence interval, we're essentially computing K, right? So our value for K is going to be C times sigma divided by square root of N. Okay. All right, so we have sigma for this problem. Our sigma is half a centimeter. We have N. N is the square root of, or N is 10. Okay, so we take the square root of 10. The only thing we don't have yet is C. Okay. All right. But for C is very easy to look up. So let's look this up in the table. Okay. And we have a degree of confidence of 95%. Okay, so we're going to look up in the table for gamma is equal to 0.95. Okay. All right. So let's scroll back up at the table and look on the column for gamma is equal to 0.95. Okay. And we can see here that for gamma is equal to 0.95, our value of C is 1.96. Okay, so let's go ahead and plug that in. And so we plug in all these variables here. We have 1.96 multiplied by sigma, which is 0.5 centimeters, all divided by square root of 10 measurements. Okay. And what we get is a value of K of 0.31 centimeters. Okay. All right. So now that we know the value of K, we can compute our confidence interval. And so our confidence interval in this case is X bar minus K less than or equal to mu less than or equal to X bar plus K. Okay. Our X bar value is 7.5. Okay. And so we're just going to add 0.31 and subtract 0.31. Okay. And so if we do that, then our confidence interval is 7.19 centimeters is less than mu is less than 7.81 centimeters. And that is our answer right there. Okay. Okay. So fairly straightforward in this case. And so, the thing with probability and statistics in general is that most of the computations are fairly straightforward. It's just kind of, there's just a lot of kind of very specialized terminology. There's a lot of very specialized, tables and stuff like that. So, the thing with probability and statistics, how should I say, it's hard, it's difficult and confusing in a different way, and it's really unlike anything we've done in the class, where I think for a lot of things we've done in the class, they involve kind of very lengthy kind of computation procedures, whether you're looking at differential equations or Fourier or something like that. You're either doing a bunch of integrals or you're doing a bunch of algebra. Probably statistics, there's not that much math or computations to do. It's just kind of figuring out kind of where to put all the numbers and kind of what tables to look up. Okay. All right. Any questions on this example here? Okay. All right. So I want to make one note before we move on. And so, you can see from this equation up here that our value for K, depends on the number of measurements that we take, right? And so since we have n in the denominator here, the more measurements that we take, the smaller our confidence interval is going to be. Okay. And so, for this experiment, we only asked 10 people. But if we were to ask, 100 people instead, so we got 100 measurements, then our value of K will be smaller. Okay. And so with the smaller value of K, then our confidence interval will shrink. Okay. And so let's just do kind of a very quick experiment. So let's say that we asked 100 people. Okay. So let's go ahead and recompute K in that case. Okay. And so instead of square root of 10 on the denominator, we have a square root of 100 instead. Okay. And so in this case, our value of K is 0.098 centimeters. Okay. It's basically 0.1 centimeters. Okay. All right. And so with that value for K, then our confidence interval then becomes the following. So then we have 7.4 centimeters, assuming our sample mean stays the same. And so assuming our value for X bar is still 7.5. Okay. Okay. And so assuming our sample mean stays the same, which is a big assumption, right? And so, assuming our sample mean stay the same with 100 measurements, you can see that we're a lot more confident in our measurement. Okay. We're a lot more confident in our measurement of 7.5. And so you can see that our confidence interval now is between 7.4 and 7.6. Okay. So that's one thing to keep in mind. And so there are a few things that you can do to kind of improve the confidence in your measurements, right? And so the first thing that that I think people already kind of understood is to just take more measurements, right? And so that's what you see here. The other thing is you can modify the degree of confidence as well, and so that'll also modulate the value of. Okay. So that was kind of our first example for this. So hopefully that's made it pretty clear. Okay. But one thing that we assumed here, or kind of one thing that we kind of glossed over, was the value for sigma. Okay. Okay. And so in other words, we made the assumption that we knew the true value for sigma. And remember, what sigma represents is the standard deviation of our quantity. Okay. And so we assumed we knew that. We kind of based it off the uncertainty in the measurement, which is not a bad idea. And so, a lot of times your uncertainty or your standard deviation is going to be determined by just whatever you're measuring with. Okay. Assuming your the thing you're measuring is staying the same, that's not a bad assumption to make. Okay. And so, even though I'm kind of framing it in this way, usually if you have a good idea about your measurement instrument, assuming the value for sigma is not bad. Okay. Right. And it worked for this problem because I would say that a smartphone the smartphone itself is not randomly changing sizes, right? Assuming that everyone's measuring the same smartphone, and so it's not like there's uncertainty in the event that's occurring. The only uncertainty in the previous problem was in the measurement device. Okay. So there's no other uncertainty or biases in this experiment, right? And so, the smartphone is a smartphone. It has a true length. It's just whether or not we can measure it accurately or not. Okay. All right, but this situation, a situation where we know the standard deviation is not always going to be the case. Okay. And so in situations with more uncertainty, and so if you look at your commute time, for instance, right? It's hard to say with confidence what the standard deviation of that is going to be. Okay. And so, we have another procedure. We have another procedure for computing confidence intervals when we don't know the value of sigma beforehand. Okay. So let's go over that procedure now. Okay. Okay. So for many situations, okay. So for many situations, we can't assume the value of sigma beforehand, because there's just a higher degree of uncertainty in what we're measuring. Okay. Okay. So let's say that there's a higher degree of uncertainty in the experiment. Okay. All right. And so in these cases where we can't assume a value of sigma, we can of course measure it, right? And so just like we measure the mean, we can measure the variance of our samples as well. Okay. And so we can get an estimate for the sample variance instead of the true variance. Okay. So we can compute sigma based off our measurements, right? So the same way that we compute our sample mean, right? So the same way we can compute x bar, we can compute the sample variance as well. Okay. But remember, when you're measuring these things, they're not, they may not be the true value for the variance or the mean. They're just what we measure. Okay. It's just what we measure, right? So what we measure and what it truly is are different things. Okay. Ideally we'd want them to be close, and most of the time they are fairly close, but it's important to make that distinction that the true value of sigma is a property of the underlying random variable, right? And so that's kind of, you can almost think of it as like the truth of the world. Okay. Oh, my cat's back. Oh, okay, bye kitty. Whereas what we measure, that's just kind of what we observe, and so those two things can be different. Okay. And so in this situation, when we're relying on the sample variance, we have to kind of change our procedure a little bit. Okay. 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 So the procedure is the following. Okay. And so we're going to start the same way, and so the same as our previous method, we're going to select a degree of confidence. Okay. And so our degree of confidence is given by gamma, right? And so we're going to express it as a percentage. Okay. Okay. The next step, we're going to take that degree of confidence and compute a certain value. Okay. All right. And so the value that we're going to compute, or the formula that we're going to use 0.5 multiplied by 1 plus gamma. Okay. So we're going to take our degree of confidence, add 1 to it, and then divide by 2. Okay. And what this is going to give us, it's going to give us a value called f of c. Okay. So let me box this formula here because it's important. Okay. All right. So this f of c, essentially what we're doing, kind of the same as we did in the previous example. We want to compute a value for c. Okay. Right. It's just that because we're relying on the sample variance instead of the true variance, okay, or the sample standard deviation or the true standard deviation, the way that we compute c is going to be different. Okay. Okay. So this right here, this is going to be used to compute c. Okay. All right. But in order to compute C, not only do we need this f of C value, we also need to know the degrees of freedom. Okay. And so our degrees of freedom, I'll call that DOF. Okay. This is equal to n minus 1. Where n here, n is our number of samples. Okay. Or in other words, just the number of measurements that we took for this experiment. Okay. Okay. All right. So with those two quantities in hand, so with f of C and degrees of freedom, okay, we can look up our value of C in a particular table. Okay. Okay. So remember, we're basically looking up the value of our confidence multiplier. Okay. And so we're going to look up the value of C using something called the t distribution. Okay. Okay. And so you can look this up in a table. And so I have a table in the notes, but this is based on the old version of the textbook. So if you're using a new version, it might be a different table. But you can also look this up online too. And so if you look up the table for the I guess the full name for it is the student's t distribution, or just the t distribution, usually fine. Okay. But if you did end up getting the same version of the textbook that I used back in 2019, this is table A9 of the appendix. Okay. And so for the exam, if I do give you a problem like this on the exam, I'll give you the t distribution table, so you don't have to memorize it or anything, and don't waste space on your cheat sheet with it, because I'll give it to you. Okay. All right, but just to kind of give you a preview, the table kind of looks like this. Okay. All right, and so on the first column here, we have our values for f of C. Okay. Right. So we have a row for 0.5, 0.6, 0.7, 0.8. Okay, so on and so forth. Okay. And then for all the other columns, this is going to be our degrees of freedom. And so maybe let's say we have 1 degree freedom, 2, 3, 4, 5, 6. Okay. Right. So everything up here, these are the degrees of freedom. Okay. All right. And then in the table, what you can look up there are all the values of C. Okay. So let's say that, for the first row here, for a f of C of 0.5, they're actually all zeros. Okay. But for the second row, if you have an f of C of 0.6 and a degree of freedom of 1, and you have a C value of 0.32, okay, and then it kind of goes on from here. Okay, so I'm not going to write in all the values of this table, but you can see it in the notes. Okay, maybe I'll do one more row. Okay, so you don't have to write down all the values in this table, because this is just an approximation to definitely use the one in the notes. The one in the notes is a bit more filled out, but basically the way you use this table is that you look up the row for your f of C. Okay. Then the column that's associated with your degrees of freedom. Okay. Then in that column and in that row, that's going to give you your value of C. Okay. Okay. So that was a lot of work, a lot of tables to look up just for, the value for C. Okay. But from here, our method kind of goes back to kind of what we did before. Okay. So with our value of C in tow, we can use this to compute K. So what step are we on? Step 5. Okay. Step 5, compute K. Okay. All right. So our value of K, this is going to be C times S divided by square root of N. Okay. There is one subtle change here. So S here is our sample standard deviation. It's not the true standard deviation anymore. It's the sample one. Okay. All right. And then step 6. Step 6 is just to display our confidence interval. All right, so our confidence interval, just like before, is x bar minus k less than or equal to mu less than or equal to x bar plus k. Okay. All right. And so, from when you look at it from the end right here, it looks like it's the same. But when you don't have the true value for the standard deviation, we have to change our value for C just because our confidence multiplier is going to be modulated based on that. Okay. And that's basically just reflecting the fact that what we measure for the standard deviation, we have a lot more uncertainty in that compared to the last one. Okay. And so our value for C needs to be modified as well to account for that. Okay. All right. Any questions on this before we jump into an example? Okay. All right, so let's go ahead and do an example just so you can see this in action. Okay. And so this example will be a little bit more engineering related compared to the previous one. So let's say that we've performed experiments to measure the flash point of diesel oil. Okay. And so let's say that we obtain the following measurements. Okay. So let's say we obtained a measurement of 144 degrees Fahrenheit. We obtained a measurement of 147 degrees Fahrenheit. Okay. Then we've got 146 degrees Fahrenheit, 142, and 144. Okay. So we only have 5 measurements in this case, and usually this is kind of the case. And so for an engineering experiment, usually these are pretty expensive to set up, and so a lot of times you're not going to be able to get a ton of measurements, and so you're not going to be able to measure this 100 times. Okay. And so our confidence interval becomes a lot more relevant here because in a setting where we have a finite number of measurements, it's going to be clear, it's going to be really important to to express how confident we are in these. Okay. All right. And so from these measurements, noting that we don't have a known standard deviation. Okay. What we want to do is we want to compute the 99% confidence interval for these measurements. Okay. All right, so we're going to compute this 99% confidence interval. Okay. Okay. So let's just kind of follow the same recipe that we had, that we just talked about here. Okay. But before we jump into that recipe, we need to actually compute, what the sample mean and the sample variance, and consequently the sample standard deviation is going to be. Okay. All right. So sample mean. Okay. So X bar. Remember, X bar is the number 1 divided by n summation from 1 I is equal to 1 to n of xi. Okay. So we just add up all of the measurements and then divide by n, right? And so if we do that for this one, we add up, all 5 measurements, we divide by 5, we get a sample mean of 144.6. Okay. All right. Next, we can compute our sample variance. Okay, so we don't have an equation for sample standard deviation, but we can take the sample variance and just take the square root of that. Okay. All right. So remember, the formula for sample variance is 1 divided by n minus 1 summation I is equal to 1 to n of x bar minus xi squared. Okay. All right. And so if we do that for these measurements, and so normally you would punch this into a calculator and compute those. We would get a sample variance for this problem of 3.8 degrees Fahrenheit square. Okay. And so if we take the square root of this, S, it actually ends up being almost half. And so our sample standard deviation is 1.95 degrees Fahrenheit. Okay. Okay. All right. So with those in mind, let's go ahead and compute our confidence interval. Okay. All right. So first thing we have to set is our gamma value. So our gamma is our degree of confidence. Okay. So for a 99% confidence interval, our degree of confidence is 0.99. Okay. And so after we set our degree of confidence, the next thing is to compute is f of c. Okay. All right, so f of c, our formula for that is 0.95 or 0.5 times 1 plus gamma. And so for this problem, that's going to be a 0.995. Okay. All right, so next thing we're going to compute is our degrees of freedom. And so our degrees of freedom is just our number of measurements minus 1. Okay. And so for this problem where we only have 5 measurements, our degrees of freedom is going to be 4. Okay. Okay. And so for this, problem, now that we have our f of c value and our degrees of freedom, we can use the t distribution to look up our value for c. Okay. Okay. And so if we look this up in a table, then what we get is a c value of 4.6. Okay. Yeah. Hey, stop destroying the carpet, you little shit. Sorry, my cat was destroying the carpet as usual. Okay. All right. So now that we have the value for c, we can compute k. Okay. So K is equal to C times S divided by square root of N. Okay. Right, so we have all of these values, and so we have the value of C, we just computed that, it's 4.6. We have S, which is 1.95 degrees Fahrenheit, and our N here is 5. Okay, and so we plug all that in, we get a K value of 4.01 degrees Fahrenheit. Okay, right, and then finally, we'll go ahead and use this to compute our confidence interval. Okay, and so our confidence interval is just our original measurement, sample mean minus K, to our sample mean plus K. Okay, and so for this, it's 140.5 degrees Fahrenheit less than mu, which is less than 148.7 degrees Fahrenheit. Okay. All right, any questions on this example here? Okay. All right, so that's confidence intervals. And so, we basically have two different recipes, depending on if we know the sample, the standard deviation beforehand, right? And so if you know the true value for the standard deviation, it's a little bit more straightforward just because there's less tables to look up. But if you have to compute the standard deviation, you would use the second recipe here. Okay, so there's kind of two different ways, but essentially, the goal is the same. And so the goal for both procedures is to compute the value of K, and then that K is going to give you your confidence interval. Okay. Okay. All right. And so, we have 10 more minutes of class left. And so I did want to start the next topic just because the next topic is a little bit lengthy. Okay. So I want to make sure that I kind of finish it, before we, before the end of the week. And so let's talk about hypothesis testing. Okay. Okay. All right, so this is kind of a new topic. It's still kind of within the realm of probability and statistics, but now we're kind of getting more into kind of experimental design. Okay. Okay. So what is a hypothesis? Okay. So hypothesis is undoubtedly a term that you've heard, probably millions of times in your education of science and math. Okay. But we're going to use kind of a little bit more narrow definition here. Okay. And so for the sake of, for our cases, we're going to define hypothesis as the following. Okay. And so hypothesis is a theory or a guess about the numerical value of an unknown quantity. Okay. So basically, before you perform an experiment, you have to form a hypothesis in terms of, what you expect that to be. Okay. So let's go back to our previous example, right? And so for the previous example, we performed an experiment to determine the flash point of diesel oil, right? And so maybe before the experiment, what we can say is that, we can form a hypothesis that the flash point of diesel oil is about 145 degrees Fahrenheit. Okay. So this is an important quality of any experiment, right? And so, a lot of times, when you're performing, engineering experiments, which normally are very kind of costly and time consuming to carry out, you have to have some kind of idea of what you expect to find from the experiment. Okay, so you're not just taking measurements just for the hell of it, right? And so, a lot of times you have to have some kind of guess, and with the idea that the measurements that you are taking are going to be to either verify your hypothesis or to disprove your hypothesis. Okay. Okay. And so whenever you form a hypothesis for an experiment, they need to be tested in order to verify, whether it's true or not. Okay. And the way that we test it is we perform experiments, we gather measurements. In other words, we gather evidence on whether, the hypotheses are true or not. Okay. Okay. All right. And so that's what this section is going to be all about. And so this section is I think everyone kind of understands, just by taking labs and just by being in math and science for as long as you guys have, I think everyone kind of understands the idea of a hypothesis and the need to verify it through an experiment. And so we're not really going to be breaking the mold here. And so it's these are all concepts that I think everyone should be aware of. I think what I do want to express here is kind of more formalized theory in terms of how do we actually do this in kind of in an engineering context. Okay. How do we say mathematically that whether a hypothesis is true or not based on the measurements that we obtain. Okay? And so this section here goes kind of hand in hand with the previous section in terms of confidence intervals, right? And so for confidence intervals, we saw in the previous section that the more measurements that we obtain, the more confidence we have in our results. Okay, same thing is going to apply here, right? And so when we perform an experiment, when we perform measurements, we can say with confidence whether our hypothesis is true or not. Okay, because remember, throughout this, the theme throughout this entire section here is that almost everything that we observe in reality is subject to some kind of uncertainty, right? Even in things that you think are very certain, there's still some variance in terms of that. And so, how do we deal with that uncertainty? How do we factor that into our computations? Is really important, especially for cases where there's a lot of uncertainty. Okay. And so for the last 4 minutes, I'm going to we'll start an example. We definitely don't have enough time to go through all of it, but just to kind of give you an example of why something like this is important in engineering. Okay. Okay. And so for this one, for this example, let's say that we are looking to purchase a set of structural wires. Okay. Okay. Right. So a structural wire is just kind of a thin piece of metal that's used to kind of support a weight. Okay. All right. And so from the supplier, they claim that these wires they can sustain a load of 200 pounds. Okay. Okay. Or in other words, you can hang a 200-pound weight from these wires, before they end up breaking. Okay. All right. And so the reason we're purchasing these wires is that, we're going to use them to hold up something that actually is going to weigh 200 pounds. Okay. Okay. So basically, we're going to be pushing it right up to the breaking point. Okay. And so what we want to do is, before we actually commit to this, and so let's say that we need to purchase, maybe like 300 yards of this for our application. So let's say that we're using it for something big. Okay. Before we commit to that, we actually want to verify whether this supplier's claim is true. Okay. Because a lot of our job, a lot of our design is riding on the fact that these wires can actually sustain that load. And so since they're playing such an important role, we want to make sure that, when we purchase these wires, they're actually going to do what they say they're going to do. Okay. And so we're going to run an experiment to see if this is true. And then based on the results of the experiment, we can either, prove our hypothesis that these wires are good, or, or we can, have our alternate hypothesis that these wires are shit and that we shouldn't buy them at all. Okay. All right, but we'll do that next time, just because we're just about at time today. Okay. All right. Any final questions before we wrap it up for today? Okay, all right, so that's all we got time for today. So I'll be back on Thursday, and I'll have your exam, so you can come pick it up on Thursday. So thank you guys for coming today, and thank you guys for being flexible today on the virtual instruction. So hope you guys have a good rest of your day, and I will see you on Thursday. Thanks, guys. All right, Lillian, any final questions before I close the call? Okay, all right, I will see you Thursday.